Hello, we're going to try to do another recorded lecture for PHI 512. This time we're going to talk a little bit more about sampling distributions. Again, this is not an R lecture, this is a lecture on biostatistics content. So let's return to our remdesivir example for this discussion. So in that remdesivir study, we were looking at patients with severe COVID were given this 5-day course of remdesivir. For each patient, clinical condition was assessed or measured after 12 days, and we looked to see for each patient if they had um, improved by 1 point or not. So, of those patients on this study who all received remdesivir, roughly exactly 146 out of 191 of those patients were seen to experience at least a 1 point improvement in clinical condition at day 12. And we are treating this as a binary outcome. Um, and we're imagining we know this sort of historical rate that for similar patients who do not receive remdesivir, roughly 66% will experience such an improvement. And so now the question is, does this indicate that remdesivir seems useful, at least with regard to this outcome? And again, this was taken from a study that was run earlier, modified slightly. These numbers are slightly different, and there was a control arm, but I've modified and simplified things for us to engage with so far in this course. So when we think about doing statistical inference here, generally null hypothesis testing reduces to this question: how does this 146 out of 191 patients that we observed improvement for compare to what we might expect to see if remdesivir had no effect? So in this sort of imagined null hypothesis world where remdesivir has no effect, and in fact each patient has a 66% chance of improving as if they had not taken remdesivir, is observing 146 out of 191 unusual? Um, so again, to answer this, we looked at a sampling distribution for the number of people out of 191 who improved, and we did this in an imagined world where each patient had a 66% chance of improving, right? This is the world we imagined corresponding to our null hypothesis. And we looked at that sampling distribution, and we're going to compare that to our actually observed 146 out of 191 patients improving. And we'll engage with why some of the text is yellow and some is blue in a moment. So again, this was the sampling distribution that we looked at. We related this to flipping a coin. If you flip a coin 191 times, and each flip, the coin has a probability of heads of 0.66, so it is a weighted coin, not a usual fair coin. How many heads might you expect to see? So this is the sampling distribution of the number of heads you might expect to see. It's centered, I forget the exact value, but somewhere around 100, 130 some, I believe. And you can see that, observing values down to maybe 120 or slightly smaller, that's not super uncommon. Similarly, observing values up to 140 or so, that's not super uncommon. Observing values above 140 is pretty uncommon. This happens in a very small proportion of our simulated trials. And below, say, 115 is quite uncommon. That also happens in a very small proportion of our simulated trials. And if we were to look at this and remember that in our data we observed 146 patients responding, 146 would be very unlikely in this imagined world. So again, we talked about running hypothesis testing here. Likely we would get a very small p-value and could reject the null hypothesis that the probability of heads was 0.66. Anyhow, that was stuff we had done before. We're now going to think about sampling distributions and statistical inference in a similar way, but slightly different. So engaging with the statement with the yellow and blue text again, we said, okay, so to answer our question about whether remdesivir was effective, we created a sampling distribution, and in gold, we have the quantity that we were looking at in the sampling distribution, the summary of our study or our data. And that summary was the number of patients out of our 191 who improved. So that is our summary we are interested in. And we engaged with that in this, in an imagined world. We engaged with that in an imagined null hypothesis world where each patient had a 66% chance of improving. So again, we've broken this into two parts. We have the summary that we are looking at in our sampling distribution and the world under which we are generating our sampling distribution. The summary is in yellow, the world is in blue. So again, our summary here is the number of patients who improved out of 191, and we look at this and see if it is evidence for or against the null hypothesis. Another way to look at this same summary, rather than looking at the number of patients who improved, we could actually look at the proportion of patients who improved out of 191, right? This is also a summary of the data in our study. And this summary could push us in favor of believing that we are in a world where each patient had a 66% chance of improving, or push us to believe that that is not the world we live in. So let's look into that a little bit more. So again, let's think about using as our summary the proportion of patients who had improved out of the 191 patients, rather than the number. So in this case, we would see that in our study, since 146 patients improved, that was a proportion of 0.764. So, 76.4% of the patients in our sample improved. And so now when we calculate a sampling distribution, again, we're going to live in an imagined world where each patient has a 66% chance of improving, but now we're going to look at the proportion of patients who improve on each study rather than the number who improve. So if we go to the bottom, I think this statement, this is what we're thinking about when we engage with the sampling distribution. Okay, if each patient has a 66% chance of improving, that's the world we're imagining, what proportion of patients out of a sample of 191 might we see improve? So how do we do this? How do we get this sampling distribution? So again, exactly now we're calculating a sampling distribution for the proportion of patients, proportion, not number, of patients out of a sample of 191 who improve when each patient has a 66% chance of improving. So we're going to reduce this to a coin flipping problem. So to get this sampling distribution, what do we do? So we run a large number of experiments, just like we did before. In each experiment, we again flip a coin 191 times, and this coin should have a probability of success of 66%. So we find our weighted coin, we flip it 191 times, and we record now not the number of heads that we flip, but the proportion of heads that we flip. After recording all of those experiments, we make a histogram of all of those proportions, and that's our sampling distribution. And again, often we won't do this by hand. We'd first need to find that biased coin before we could flip it if we did it by hand. We'll have R do it for us. But let's again look at what this would look like if we did it by hand. So in trial 1, we flip the coin 191 times, we get 103 heads. Great, we don't report 103 now, we report 103 out of 191, which is, as a proportion, 0.54. So this is saying in this trial, 54% of our sample improved. We do it again. We flip 191 times. We look at the number of heads, but we record not the number, but the proportion of heads. 98 out of 191, is 0.51. And we keep doing this. Each time we run a trial, we flip that coin, we calculate the proportion of heads, and we report that. After maybe 1 million trials, we have all of these proportions of heads, and we can look at a histogram of the proportions of heads on all of those trials. And in this case, when we look at this histogram, what we see is the histogram is centered at 0.66, right? Because that's the probability of heads, so maybe that should be the center of this histogram of proportion of heads we see. And we see on some trials we get as low as 60% or even maybe down to 55%. So of those 191 flips, on some trials as few as 55% of them are heads. On some trials, as many as 75% of them are heads, although it's pretty rare, right? Generally, maybe in most trials, it's between 60% and 70% that we observe heads. Great. So again, as expected, this sampling distribution is centered around our true probability of heads. One thing to note, this looks a lot like our sampling distribution when we looked at the number of heads as opposed to the proportion of heads. And in fact, the two are identical except for the axis labels, right? If we take the axis proportion of heads and multiply by 191, we get exactly the number of heads that we flip in each of these trials. So again, they should be identical. We've just basically rescaled the x-axis, right? One is like a proportion of 191, and the other is, again, a count of 191. So what this means in general is that all of the hypothesis testing we did before, when we engaged with the number of people who got better or the number of heads, we will get the exact same results if we engage with the proportion of people who got better or the proportion of heads. I think working on the proportion scale rather than the number scale is a little bit more natural. And in particular, this is because, remember, we talked about parameters and estimators. Parameters are functions of nature. Estimators are parameters are summaries of nature. Estimators are summaries of our data. And with our estimators, we want to estimate our parameters. And if we think about a parameter as the probability that a coin will flip heads, then the proportion of times the coin has flipped heads in our study flipping the coin is the natural estimator for that parameter. So again, the proportion of patients who improve in our study is the most natural estimator of the probability that a patient with characteristics like those on our study treated with remdesivir will improve. So the proportion is the natural estimate of the probability, which is that parameter we're interested in. So in the coin model, maybe a simple example will help. Imagine our friend gave us a trick coin. We don't know the probability it flips heads. We're pretty sure it's not 50-50 though, and we want to estimate it. If we flip the coin 1,000 times and see 715 heads, the proportion of heads is 0.715, and that's also our best guess as to the probability that the coin flips heads. We would say for each flip, we believe the probability is at least close to 0.715. So again, by looking at this sampling distribution, we could run a hypothesis test. We could say, okay, so in our data, we observed a proportion of 0.745, right? This is what we might have observed in a world. The sampling distribution is what we might have observed in a world where the probability of heads is actually 0.66. 0.745 is really big compared to 0.66. Compared to this world where we might have, this world where the true probability is 0.66. So again, if this is the range of probable outcomes, we see that 0.745 is well into the tail. In very few of those trials did we observe a proportion as high as 0.745 of patients improving. So again, we have run this hypothesis test when we looked at number of patients improving rather than proportion, and it turns out if we think about things like p-values, the p-values will be the same because the area of the histogram to the right of this line here is the same as the sort of area or proportion of the area of the histogram to the right here. Again, we're just rescaling the x-axis. That's one way to think about it. So again, here, our null hypothesis would be the probability of improving on remdesivir is 0.66, or pi, if we're calling that pi, is 0.66. And if we ran a hypothesis test of this null against either a one-sided or two-sided alternative, we see that our conclusions from both of these would be the same. It would result in the same very small p-value, and so in general, we'd have to state the level and then actually calculate our p-value, but we could generally reject the null hypothesis here, noting, again, if we're looking at proportion, that it's very unlikely, if the true probability of improving was 0.66, that we would observe a proportion of patients improving as high as 0.745 in our sample, right? 0.745 is statistically significantly bigger than 0.66 based on observing flips from 191 coins. We also talked about calculating critical values before. How do we calculate critical values for tests? We look at our sampling distribution and then look at quantiles of that sampling distribution. And so here, again, we could identify two proportions such that only 2.5% of trials fall above those proportions, and 2.5% of simulated trials fall below that lower proportion. So again, these would be our critical values for a level 0.05 test based on the proportion of patients improving. We could do the same thing with the number of patients improving. And again, we have like a ton of similarity between these results. Again, the critical values for the number are numbers of patients. Here, I think it's 126 and 139. If we see more than 139 or fewer than 126 patients, then we would say the response probability on remdesivir is not 0.66. Similarly, whatever these proportions are, if we see below, it's something like 0.58 proportion of patients improving, or above something like 0.72 proportion of patients improving, then we would say the response probability on remdesivir is not 0.66. We have enough evidence to reject that null hypothesis at the 0.05 level. All right, so I think big picture, what we have done is we have moved from using one summary of our data, the number of patients who improve, to using another, the proportion of patients who improve. And so often when we think about hypothesis testing in the future, we're going to have to think about what the right summary of our data is that either gives us evidence in favor of the null hypothesis or evidence against the null hypothesis. And for different types of hypotheses, this summary will be different. Great. Now, the next thing I want to cover here is thinking a little bit more about these sampling distributions, and in particular, the sampling distribution of the proportion of heads, not the number of heads, but the proportion of heads, and not think about it for the sake of hypothesis testing, which is what we just did, but just think about what happens to that sampling distribution as we flip the coin more times or flip a coin fewer times. So, all right, let's run a thought experiment. Let's imagine I have a fair coin, 50-50 probability of heads and tails. I flip it 10 times and record the proportion of heads. So that's an experiment I could do. We could imagine doing that a large number of times and looking at a sampling distribution for this proportion of heads. I'd only flip the coin 10 times. I may even get 10 out of 10 heads from a fair coin. That's probably pretty unlikely, but 8 out of 10 heads doesn't seem that unlikely, which would result in a proportion of heads equal to 0.8. Fairly extreme compared to the 0.5 probability of heads. So this is what our sampling distribution looks like here. And again, we see some pretty extreme values. We see values, as large as 0.9, as small as 0.1. Maybe if I made a couple more, more bins here, we could even see if we'd seen actually many 1.0s or zeros. It's pretty spread out though. Let's imagine we run the same experiment with the same coin, but now we flip it 100 times and record, I should say the proportion of heads, but record the number of heads. You can imagine again, do we miss to identify a sampling distribution for the proportion of heads? Again, each of these experiments will flip the coin 100 times and record that proportion of heads. So what do we see? Again, we see a proportion of heads centered around 0.5. That makes sense. But now we're seeing that out of 100 flips, you're rarely going to get 80 heads or 90 heads, right? That somehow seems much more unlikely. And in fact, this sampling distribution reflects that. In fact, here, our proportion of heads will generally be between 0.4 and 0.6. Generally, in our sample of 100 flips, we will see no fewer than 40 heads or no more than 60 heads, again, with a fair coin. So again, this distribution is a little less wide, a little more narrow than the previous. Imagine we do the same thing, and now instead of flipping it 100 times, we flip it 1,000 times and record here I should again say proportion of heads. Again, we could look at a sampling distribution for this proportion of heads. This experiment would take a long time for us to run. For each experiment, you'd have to flip the coin 1,000 times to get one sampled proportion of heads. You'd have to do that experiment many, many times in order to come up with a sampling distribution. But again, we can do this very quickly in R. And what do we get? We now get this sampling distribution that is even more finely, more closely gathered around 0.5, the probability of heads. We basically never see a proportion less than zero point 0.4 or greater than 0.6, and in fact, it's even closer to 0.5 than that. Probably everything is between 0.45 and 0.55, right? The proportion of heads is very concentrated around 0.5. Very likely you will get roughly 50% heads and 50% tails. We could even make this crazier and go up to 10,000 flips, again recording the proportion of heads, and here we see that this is even more concentrated, right? So I'm just going to run through all of these in reverse. We have 10,000 flips, the proportion of heads is super concentrated around 0.5, 1,000 flips less concentrated, 100 flips less concentrated, 10 flips not concentrated at all, still probably centered around 0.5, or it really should be. This histogram is a little left shifted, but centered around 0.5, but again, not concentrated at all, right? And so what we're finding is as you increase the number of times you flip the coin, the width of your sampling distribution decreases. And this is basically just saying, as you flip a coin more times and look at the proportion of heads, you will get a more and more accurate estimate of its probability of flipping heads. And this is true in general. If we want the most accurate estimate of a population parameter that we can possibly get, we want to collect as many samples as possible, right? The more samples we collect, the more precise we will be in estimating this feature of the population we're interested in. Another thing that happens is if you are trying to identify if a coin is fair or if a coin is not fair and run a hypothesis test, in order to find statistical significance, smaller and smaller differences will actually give you statistical significance. So what do I mean by that? So if I have a coin and I flip it 10 times and I get 7 heads, I probably I probably should claim. I mean, I probably should not claim that it is a weighted coin. Sorry for that typo. I probably should not claim that it's a weighted coin, right? It's very reasonable with a fair coin that I would get 7 of 10 heads. That's not an unreasonable scenario. However, if I flip a coin 1,000 times and get 700 heads, that's an incredibly rare scenario if it's fair. In fact, we can just look at the sampling distribution. There is no visible weight at 0.7. That is how unlikely it is. I think I ran 1 million trials, 1 million experiments here, and I don't think I saw a single one where, in fact, I'm sure I didn't see a single one out of all of those where I had observed 700 or more heads. So that would never happen if the coin was fair and I flipped it 1,000 times, but it would happen some amount of the time if it was fair and I flipped it 10 times. So again, if I have fewer flips, then it's much harder to identify that a coin is not fair. Whereas if I flip it a ton of times, I can really precisely identify whether the coin is fair or not. And smaller deviations from fairness will still result in statistical significance. So the last thing I wanted to talk about is one reason that we like the standard deviation. So we talked before about measures of spread, and that's actually quite useful here as we are intuitively observing that this distribution has less and less spread as we flip the coin more and more times. And the standard deviation was one measure of spread we had talked about, as well as the mean absolute deviation and the interquartile, right? So we can talk, just like we talked about spread of distribution originally, we can do the same thing with sampling distributions. We can think about the spread of a sampling distribution, the standard deviation of a sampling distribution, for example. And we see that there's this really beautiful and convenient mathematical relationship for the standard deviation of sampling distributions as we think about increasing the number of samples we collect. We're going to talk about this with regard to coin flipping and proportions, but it actually is a much more general phenomenon. So if we look at the standard deviation of this distribution, we find that it is 0.5 over the square root of 10. And I'm going to call that SD10, the proportion of heads from 10 flips of a fair coin. If we then look at the standard deviation of this distribution, which is a little narrower, we find that it looks kind of similar to the previous. It is 0.5 over the square root of 100. If we look at now the standard deviation of this distribution, right, the spread is even smaller. It is 0.5 over square root of 1,000. And finally, if we look at the standard deviation of this distribution, it turns out, again, mathematically, one can show this, that it is 0.5 over the square root of 10,000. Oops, and I have extra equals on all of those lines. Sorry for the typos. So what is happening? So we know the standard deviation should decrease as the number of coin flips increases, right? Because the width of that sampling distribution should be decreasing. But this is a really cool mathematical relationship. The width of the standard deviation of our sampling distribution, the standard deviation of our sampling distribution decreases exactly like the square root of or 1 over the square root of our sample size, right? So if we put if we did 1,000,000 flips, what we would have for the standard deviation is 0.5 over the square root of 1,000,000. So that allows us to very precisely identify how the width of the sampling distribution decreases with the number of coins we flip, or the number of times we flip a coin. And in particular, we are characterizing width here with standard deviation rather than mean absolute deviation or interquartile rate, because there's not as nice a mathematical relationship between those as there is with this standard deviation. One last piece of statistical language, I'm going to call it. So in this example, we were trying to estimate the probability of heads, which is a parameter of nature, in this case, of our coin, with the proportion of heads, which is an estimator based on our sample. So we looked at the sampling distribution of the proportion of heads. This is the sampling distribution of an estimator. And we looked at the width of that sampling distribution by thinking about the standard deviation, the SD. This standard deviation of a sampling distribution of an estimator, or you can just say the standard deviation of an estimator, has a special name. It's sometimes called the standard error. So if someone says, here is my estimate of the, or here is the proportion of heads in my sample, the estimate of the probability of heads, and here is its standard error, they're meaning here is the standard deviation of that estimator, right? And it's telling you something about the precision of the estimator. Great. So I'm going to end this here. I hope this video is helpful. We will probably pick up next with confidence intervals.